Okay, let's solve this um, beam here. We have a beam of 10 feet long. It's pinned on one point, and there's a roller on the other point. What this means is that a roller can only, you can only place a vertical load on a roller as it's just going to support that. There is no, it won't be taking anything from the left or right because the name suggests that it just takes a vertical load. It just, the whole purpose of the roller is just for the load to sit on top of it. Now, a pin does take vertical load and it takes axial load. But as you guys can see here, there is no axial load acting on this beam at all. Everything is just coming from either the self weight or the beam of the beam or any load placed on top. So as a result, there is no uh load going in the X direction that the pin is taking. But there is a load for both the Y direction for both A and B, for both the pin and the roller. So let's find out what these values are. So what kind of loading do we have? We have 500 pound per foot. That means for every foot that you travel along this beam, another 500 pounds is getting added, right? So every foot is 500 pounds. And we could solve this numerous ways. We could do this the long way, and we could do this the long way, and also, given the geometry of what's going on too, there's an easy way. So how about we go through the long way first so we can kind of see how we could do this process-wise, and then afterwards, we'll go the easy route geometrically to see why the easy route works. So my step would be to take a point about the beam, which ideally I would pick A. So some of the moments about A, um, I have my counterclockwise going positive. So whatever is going to tilt my beam in the positive direction, counterclockwise, it's what's going to be positive, right? So right now, as of right now, we're assuming that By, which is the vertical reaction, is going to be pushing counterclockwise. So I'm assuming this. Now, I could have assumed the latter. I could have assumed that it's going to be pulling it, but because of how, when you're thinking about this problem, you know that this load is landing on top of this. So there's going to be an equal and opposite reaction given by By, which is versusing this reaction, this loading on top. So this is why I chose for By to have its direction pointing upward, counterclockwise. Hence, why when I start summing the forces, you'll see why. So now, okay, so the next step would be 500 pound per foot. We need to somehow simplify this loading. And what I'm going to do is I'm going to take this loading, this uniform load, and turn it into a concentrated point load. How do you do that? Well, as you can see, the shape of this loading is it's a rectangle. And when you take the area of a loading like this, you'll get the magnitude. So let's do it. What's the area here? So it's a rectangle, so it's 500 times however long the loading is, right? So it looks like it's 10 feet. So, and because of how it works centroidally, the concentrated moment of 5,000 pounds would be in the center of this rectangle, right? So if you were to hold the rectangle of this large, the mass weight of this whole thing, you would presume to hold it in the middle, because if you hold it on one side, you'd get tilt over. So this is why this centroidal location works, because for a square, for a rectangle, anything that is symmetrical in this case is going to be in the center. This is the centroid. This is where the centroidal force is going to happen. So now we simplified this force, and it seems like it's happening right there, 5 feet away from the point of A. So it's going to be negative 5,000 pounds because it's 5 feet away times 5 feet away, because moment equals force times perpendicular distance. So negative 5,000 times 5 plus because this BY, I'm assuming to point counterclockwise. Let's see, it's 10 feet away. BY, we're trying to find out that reaction. So now, what's 5,000 times 5? That's 25,000 plus 10 BY equals 0. Now, this is just straight algebra now. You put the 25,000 on the other side, make it equal to 10 BY. You divide by 10, and that should give you your reaction for BY. Let's divide by 10. So here I'm getting BY equal 2,500 pounds. Now, if this equals 2,500 pounds, and the whole load of what's happening is 5,000 pounds, as you can see, it's half of it. So one would assume just by, you know, equilibrium that the other side is also 2,500 pounds. Now we could do this by visually seeing that, or we could do this by summing the forces in the y direction. Now, let's see what's happening here. We have, let's say we didn't know, we didn't assume that just by that law that the forces cancel out. We can do it by this way, right? If you were to see the vertical loading only, which is negative 5,000, you add the reaction that you just saw for 2,500, but you're missing the AY component. Now, essentially you solve for it. So what is this value? This is negative 25 plus AY equals 0. You put it on the other side. Now you know that AY equals 2,500 pounds. And that's how you solve it the correct and long way, and preferably the way that shows the most work. Now, to solve to solve this the easy way, you could assume the geometry. So this beam is 10 feet long. It's a uniform beam, the loading doesn't change, and you know that it's 5,000 pounds when you take the resultant of this uniform load. If you know that this is happening in the middle, then you could safely say that each side is going to take equal amounts of force. The e- So that means each side will be taking half of the whole magnitude of the force. Now, only for these uniform symmetrical beams can you assume these type of values. Others, where the point load might be over here, 2/3 away, 1/3 away, you can't assume that. You would have to solve it the long way. Okay, that's it for this video. Thank you.